In this video, we're starting section 1.5 on nested quantifiers. So nested quantifiers involve propositions where we have multiple quantifiers floating around, so one inside of another. Our goals are to determine the truth values of these nested quantifier statements, recognize when nested quantifier statements are equivalent, and then we'll do a bunch of practice where we have to either convert logical statements involving these nested quantifiers into English sentences, or the other way around, convert English sentences into logical statements involving nested quantifiers. Okay, so this video, I want to focus on giving an introduction to these nested quantifiers. So I want to consider the following example. Let's let the domain of x and y be the reals. So this R is the symbol for the reals, where I write a capital R that's got two vertical lines like this. And then there's a typo here. There should be one more L in recall. So recall that this symbol, kind of looks like an E, means is an element of. So when we write something like this, it means pi is an element of the reals, or pi is a real number. Okay, so here are a couple of statements. The first one says for all x, and then in parentheses, for all y, xy equals yx. So how do I say this in words? Well, first we have a for all x. So for all x, and the domain of x is the real, so for all x element of the reals. And then I have a for all y, so how do I put those together? Well, I would say for all x in the reals and for all y in the reals, comma, and then we're asserting this equation here. xy is equal to yx. So for all x and y in the reals, x times y equals y times x. And that's a true statement. That is a true statement. This is essentially saying when you switch the order in which you multiply two numbers, you're going to get the same thing. It's the commutative property. Okay, what about if I switch the order of these quantifiers? So let me just close this statement, these quotes. So this one is now saying for all y in the reals, and then after that I got for all x in the reals, and then it's asserting the same equation, xy equals yx. Okay, well, that's essentially just saying the same thing. It's just changing which variable I introduced first, y or x, but it doesn't make a difference in terms of what this statement is saying. So this is also just true. This is also just true. So these have the same meaning. Same meaning. Okay, so as a result, these two propositions, they are equivalent. Okay, so one of the things that we are seeing in this example is quantifiers that are inside the scope of other quantifiers. And these are called nested quantifiers. Like in this first statement, this for all y was within the scope of the for all x. Because the for all x, its scope contained everything within this parentheses. So the big takeaway from this first example is that if you have two for all quantifiers, oh, and there's a typo here. This should say for all, not for all y. This should say for all t. So if there's a for all s and a for all t, and you switch the order of those two, these are going to be equivalent. These are going to be equivalent. Okay, so let's do an example involving a for all and a there exists. So this example says, let's let the domain of x and y be positive reals this time, convert the logical statement to words, and determine its truth value. Okay, so let's convert these to words. Part A is saying for all x, and the way I'm going to say it's a positive real is by saying it's greater than 0. For all x that's greater than 0, then there exists a y, which is also a positive real, so it's greater than 0. And then I'm asserting this. So I'm going to say such that, I'm just going to abbreviate such that by writing s dot t dot. So s dot t dot is the way we abbreviate such that. Okay, such that x equals y squared. X equals y squared. So for all x greater than 0, there exists a y that's also greater than 0, such that x is equal to y squared. So, well, that's true. That is a true statement. Since for any x, any positive x that we pick, for any x that's greater than 0, what would y be? Well, we would pick y to just be equal to the square root of x. And that's going to be fine to do because x is greater than 0. So we won't run into like the square root of a negative being undefined. So for example, if x was 4, then y would just be the square root of 4, which is 2. And that would satisfy this equation. Or if, let me go back to draw mode, or if x was 5.7, then y would just be the square root of 5.7. And that would satisfy this equation. Okay, so for all positive values of x, I can find a value of y. So there exists a value of y that's going to satisfy this equation. Okay, what about the other way around? What about in B? So in words, we have there exists first. So I would write there exists a y greater than 0. And then I got my for all x. So I would write such that, s dot t dot to abbreviate, such that for all x greater than 0, x equals y squared. So is it the case that there exists some positive number y where for all positive numbers x is going to be equal to y squared? Well, this is different. This is false. And the reason for that is, this is false since once y is chosen, y squared can just be one value. So once y is picked, y squared can just be one value. And that means, well, x has to be equal to y squared. So therefore, only one value of x would satisfy this equation, would satisfy x being equal to y squared. Okay, so as a result, this is false. This was claiming that there exists some y where for all positive numbers, I'm going to be able to plug in all positive numbers into this and make it true. Oh, but that's not the case. Okay, so the takeaway for this is, in general, if we switch the order of a for all and a there exists quantifier, these are not, in general, going to be the same. So I'm going to put my equivalence and put a slash through it. Those are not generally going to be the same. Okay, so I'm going to end with one final example in this video. What if I now switch to there exists quantifiers? So for this example, I'm going to let the domain of x and y be integers, and I want to convert these statements to words and determine their truth values. Okay, so part A, I got there exists x first. So this would be saying there exists, or I could write more shortly, there is an, and what is x? An integer here. There is an integer x, and then after that, there exists y. So there is an integer x and an integer y. There is an integer y such that x squared plus y squared equals 3. So there is an integer x and an integer y such that x squared plus y squared equals 3. If I really wanted to write here, like there exists an integer y or there is an integer y, I could have, but I think it's understood from context that that's what this means. So, well, is this true? If x and y are only limited to integers, can x squared plus y squared equal 3? Well, it turns out, no, this is false. And I would encourage you to pause the video and convince yourself why. Convince yourself that this is the case. Okay, it doesn't take too long to check that, but just consider a few possibilities. If I think about B and I switch the order, well, in words, this would be saying there is an integer y, there is an integer y, and an integer x, and an integer x. If I really wanted to, I could have said there exists an integer x or there is an integer x. I just think it's understood from context, such that x squared plus y squared equals 3. But these are saying the same thing. These have the same meaning. We're just identifying one of the variables before the other. So these have the same meaning here. So in general, when we have two there exists quantifiers and I switch their order, they will be equivalent. So the one that we have to be especially careful with is when there's a for all and a there exists. Switching their order definitely makes a difference.